Good evening, ladies and gentlemen. A very warm welcome to all our distinguished guests, respected engineers, academics, industry professionals, and students joining us from Sri Lanka and abroad. It is my great pleasure to welcome you all to this collaborative webinar series organized by the Sri Lanka Association of the Institution of Civil Engineers, SLAICE, together with MIDAS India. Today's webinar marks the fourth session of an exciting learning journey through an exclusive 5-part continuing professional development webinar series designed to bridge the gap between structural modeling and practical design. This expert-led series focuses on real-world infrastructure applications using Eurocodes and provides participants with integrated structural and geotechnical workflows to model, design, and verify engineering projects with confidence. Over the course of this series, participants will explore 5 practical engineering projects using 3 powerful software solutions: MIDAS Gen, MIDAS Civil, and MIDAS GTS NX. Under the guidance of premier IIT alumni and senior technical experts from MIDAS IT. We are delighted to have each one of you with us this evening. Without further ado, let us begin today's webinar on From Modeling to Design in Eurocodes of High-Rise Buildings. Ladies and gentlemen, we will now watch a brief introduction video showcasing the Institution of Civil Engineers Sri Lanka and its contribution to the engineering profession, and a short introduction to MIDAS India, highlighting its innovative engineering software solutions and commitment to advancing civil, structural and geotechnical engineering. It is now my pleasure to introduce our keynote speaker for today's technical session, Engineer Mohammad Zishan Alam. Engineer Zishan Alam is a senior technical support engineer at MIDAS India and holds an M.Tech in structural dynamics from the Indian Institute of Technology, Roorkee. His professional experience spans bridge construction, structural analysis, and the design of bridge and building projects. In his role at MIDAS, he supports engineers in carrying out advanced structural modeling, analysis, and code-compliant design using MIDAS software solutions. He has delivered technical seminars, webinars, and practical demonstrations on reinforced concrete and steel building design, bridge engineering, and real-world applications of MIDAS Gen and MIDAS Civil. With his strong academic background and practical expertise, he is well placed to guide us through today's topic, from modeling to design in Eurocodes of high-rise buildings. Ladies and gentlemen, please join me in warmly welcoming Engineer Mohammad Zishan Alam. Sir, the session is all yours.
Hello. I hope you can hear me, right?
Yes, sir, we can.
Yeah. Thank you. Thank you for confirming. So, without any further delay, I will first share my screen and then we will start the session. Just give me a minute. I hope you can see my screen, right?
Yes, sir, we can see you, sir.
Yeah. Thank you. Thank you for confirmation. So, and yeah, thank you for the introduction part. And so let's start the session now. Uh, the topic is modeling and design of high-rise building structure. And I would like to say to the attendees, thank you for joining today's session on this particular topic. And during this session, we will build up a complete picture of how tall buildings are engineered, the loads that govern them, and how a high rise differs structurally from a mid rise, and the main loading systems that we need to consider, the families of lateral load resisting systems, and the specific effects of wind and seismic action, because it's not a simple mid rise structure or a regular structure, it's a high rise one. So the governing loads are different than the regular structures. And also we need to consider the construction sequence when we are constructing the structure from the bottom floor to the top floor, how the behavior, how the boundary conditions, and how the time dependent material properties are changing. So those are the things that makes the high rise structure different from the low rise or mid rise structure. And also the most crucial part, the differential settlement of the columns. Yeah. Is there any issue? Am I audible?
Yes, sir.
Yeah, yeah, yeah. Thank you, thank you. So I was saying that the column shortening effect, the differential settlement between the peripheral and the central column, how the loads are being transferred, what is the load transfer pattern from the top to the bottom, and that is causing those differential settlement. And we are going to talk about those things in detail. And also during the session, you might be having several questions, so you can write down those questions in the chat box, and then we will address them in the end. Yeah. So let's proceed further. So here I have listed down six agendas for today's session. That is the main things to consider regarding the tall building modeling, analysis, and design part. So the first one is the high rise design problem. When we say a tall building is a tall building, and what is the main criteria that differs it from the mid rise thing, that we will be talking about. The second one is the loads and the modeling essentials. which is the
हाँ जी
foundation.
पहले तो ये था ना कि 4880 मेरे
Uh,
ख्याल में रुपीस हाँ
can
तो
you
पहले
please
मेरे
mute
ख्याल में
yourself
मैंने जो
because
क्रेडिट किया था
you
उसमें
are
मेरे ख्याल
audible.
में वो उनको क्रेडिट नहीं हुआ था ठीक है
Yeah, thank you. So I was talking about that the loads and the modeling is in modeling part, which is the very much essential, and that is basically, you can say, the foundation part of the tall building. Which actions matter? What are the loads that we need to consider? And what are the 3D analytical model that must actually capture to give us the trustworthy answer. And then we will see a comparison between a high rise and a mid rise, and how is it different, how high rise structures are different from the mid rise structures, and what are the main points there. And then we will go to the structural configuration. What are the different types of high rise structures, what are the different types of high rise structures are there, and what is the difference between them, and when should we use them and when should we not. So that is the structural configuration. And then yes, the loading part, we will go into detail of the loading part, that is the wind, seismic, time dependent effects, and how they change with the times, like the creep, shrinkage, the gaining of the compressive strength. They totally depends on the time, the construction, as the construction goes on. So how do they vary and how does it depend on that? And in the end, we will talk about the construction stage in details, in what are the theoretical parts and in the software, and then the column shortening analysis, how does it affect the design part, and the loading and analysis and interpretation of the result. And this column shortening analysis, which is the additional part which differs it from the mid-rise structure. And most of the engineers which is involved in the mid-rise one, they sometimes they never had to deal with this kind of thing, the column shortening and so on. Yeah, let's proceed further. So what makes a building high rise, and what we mean by modeling and design of a high rise structure. So this is a question that sounds simple, but it's a tricky at the same time. So there is no universal code actually, which differs or which tells us when a building is a high rise and so on. So there are like some fire codes are there, which says that the 23-meter building can be considered as high rise. Some planning codes at 8 stories. Now we will talk about the CTBUH, which is the Council on Tall Buildings and Urban Habitat, that tells us that the roughly 14 or more stories, or about 50 meters, we can say that our structure is a high rise structure, high rise building. And as we go further beyond 300-meter, we call it the super tall, and beyond 600-meter, we call it the mega tall. We can think about the Burj Khalifa, that comes under the mega tall, which is 828 meters. So something like that. Now, the height alone is not the structural trigger. The real trigger is slenderness as well. The ratio of height to base width, once that ratio passes, once that ratio passes roughly 7:1, so there something changes in the structure, and then the gravity alone does not govern the structural part. So the governing things change, and a short, like wide 20-story building can behave structurally like a mid-rise, and a slender 20-story residential tower on a small footprint can behave like a super tall problem. So that all depends on the slenderness of the building. So as I mentioned, that the 20 if this building is a 20-story and it has a wider area, then again it can behave as a mid-rise one. But if it's the area is reduced, something like that, so the slenderness increases, then it behaves like a super tall or tall building kind of thing. So that is why I want you to stop thinking of high rise as a height category and start thinking of it as a slenderness category thing. Now we are going to use the term like modeling and design. What does it mean? So modeling means building the analytical twin of the tower, the whatever structure we are going to analyze or we are going to check. We have to build the 3D representation of that captures the stiffness, mass, dynamic properties, and the construction sequence, how the construction is being done for that particular tower, and also the soil structure interaction, the boundary conditions, like the if the foundation that also depends on the foundation, like if the foundation is a pile foundation, pile cap, raft, or whatever foundation is that. So the structure and the soil structure interaction, things that needs to be considered, and we will see that in the software later on how those are things are being considered, and so that the computed response is a genuine prediction rather than a guess dressed up in a software. Now, the last thing is the design part, which is nothing but the proportioning of cores, columns, outriggers. We will talk about these terms later on. What are these terms? And foundation against a strength limits, but just as importantly, against serviceability limits. Not only strength, but also the serviceability. In the high-rise structure, strength as well as serviceability also governs very well. So that includes the drift, the comfort of the occupant, column shortening. And in a high rise, serviceability very often governs member sizing before strength does, which is the opposite of what most of us learn on smaller buildings. So that is the introduction of that part, what makes a building high rise and what we mean by modeling and design. Now, the major loads that govern a tall building. Yeah. So the gravity one. So the gravity is actually that governs majorly to the mid-rise structure and or low-rise structure, which includes the self-weight, cladding, imposed loads, and is always present and always calculated. But on a slender tower, it is rarely the load that decides the member size. So it does matter for one high-rise specific detail, loads accumulated down through the core and mega columns, and then we apply some story reduction factors when we consider the live loads over many floors, because it is statistically unlikely that every floor is fully loaded simultaneously. So we have the gravity loads, the permanent loads, the imposed loads that we consider here, that is being considered. The major one is the wind loading that actually governs that. So, and also wind has two components here, which is the wind, along wind and across wind vortex shading. We will talk about these things in later slides in detail. The third one is the seismic based on the zone where we are constructing our structure. So the seismic loads also governs that, and then the second order P delta effects. So when we have a very tall structure, so there is going to be a lateral deformation, and in that particular lateral deformation, because of the vertical loading, there is going to be a secondary effect, secondary moment or secondary forces. So that is the second order P delta effect that we have to consider in case of the tall buildings. And in the end, the time dependent material effects, that includes the creep, shrinkage, differential shortening, and construction stages, and so on, that we will be talking in detail in later slides. Yeah. So let me talk about what are the analytical model must capture. What are the things that it should include when we have to consider when we will be doing the modeling. So first and foremost, the full 3D model that includes, if we are going for the shear wall and the frames and and the cores, like the shear wall in the center of the plan, that is termed as a core, the modeling of that, outriggers, columns, slabs, all working together in one model and not a set of isolated 2D frame or analyzed separately. So that's a full 3D model that we have to generate, and the interaction, so that we can check the interaction between all of these different elements. Now the rigid diaphragms. So as we know that floors distribute lateral load between vertical elements, so we can model that as a rigid diaphragms, or based on the opening in the slab, we can model that as a flexible or semi-rigid diaphragms. So it actually helps us in distributing the load in distributing the load to the connected columns and to the connected shear walls or cores. So in the previous sessions we have already talked about how the loads are transferred from the center of mass location to the adjacent column based on the stiffness of the column and so on. So the rigid diaphragm part that we have to consider. Then the third comes the cracked stiffness. So when we go for the high rise structure, so for concrete we have to consider the cracked section properties, not the gross section. So that actually governs, that actually decides our drift and natural period. If we consider the gross cross section properties, so the drift and the natural period, they will not be actually the correct one. So we have to consider the cracked one to consider the correct drift and the natural period, and they both depend on the stiffness. And yeah, gross section, gross, if we consider the gross stiffness and so on, so they actually under predict drift and under predict the period. And then then it goes and then it goes on in our further modeling sequence, and the final result when we are going to check, they might not be the correct one. So we have to consider the codal guidelines given, and then we have to consider the cracked stiffness. The factors are given like the for beams and for the columns 0.35 for the beam and zero point 0.7 for the columns, and we can provide that as a stiffness scale factor in the beams and in the columns. Yeah. So the fourth comes as the dynamic properties that includes mass, natural periods, mode shape. Mode shapes drive both wind and seismic response. And if we get the mass wrong, say we are getting the mass calculation that is wrong, seismic mass and so on. So then what is going to be there is the, if we say we get the mass wrong, so by forgetting superimposed dead load or something like facade weight, so every dynamic result downstream is going to be wrong too. So we have to consider these parameters very well. Now the fifth one is the staged construction. We have to model floor by floor buildup so that the shortening and the lock-in forces are realistic. So when we are going from the first floor to the second floor and to the third floor, then there are already forces, locked in forces in the first floor because of the second and then because of the third. So we have to consider those locked in forces and the deformations that is actually happening to those lower floors because of the upper floors. So that can only be considered using the staged construction, and that is very much critical in the case of high rise buildings, so that we have to consider that thing. The soil structure interaction part. So again, the soil structure interaction that we have already talked about, which is the interaction between the soil properties that we will be providing as a spring support, and we will be assigning it to the pile location, to the raft location, and then we can check the interaction between the structure and the and the soil beneath that. Yeah. So second order P delta that we have already talked about, why we need this. That also second order P delta is one effect, and also if there are like the geometric or geometric non-linearity. So if we want to consider there are actually two P delta effect. One is the capital one, and the another one is the small P delta. Capital one is the global effect. Small one is the localized effect. So if we want to consider both of them, that we should be doing, so that is the geometric non-linearity that we can check on, and then we can check the behavior, the non-linear behavior of the structure, how it is changing based on the applied loading. And the last thing is the damping and the dampers. If the drift is very high and the lateral deformations are very high, so we can go on installing the dampers. So that is the tune mass dampers and so on, so that we can install. So we can apply all these options in the software using the springs option, using the general spring, using different damping options that I will be showing you in the software. Yeah, let me just go to the software how we can do that. So it's just an example of a 3D structure which is having a shear wall, which is having a shear wall, you can say that you can see that it's my shear wall here and here in the transverse direction, and in the longitudinal direction I have my moment resisting frame. So yeah, so it's that. Now which I if I go sequentially, the first one is the full 3D model, that includes core, outriggers, columns and slabs and so on. So we can model whatever is required. For the time being here, we are more interested to know what is the behavior of the structure. For the frames, we are considering the dual dual type of the building, like where we have the shear wall and the frame structure interaction between them. So here I have provided the support as a fixed support at the bottom. Yeah, here it's the fixed support at the bottom. We can just go to the boundary, and here we can provide define supports, and here we can just restrict the degrees of freedom along the translation and the rotation, and also warping degrees of freedom. And then that will be considered as a fixed support, and we can check on and check off these options to play whether I want to consider full fixity, or we want to release some degrees of freedom in some axis, about some axis. And if we have if we have a real-time stiffness of the soil stiffness from the geotechnical team, so that we can provide using the point spring support. Here we can provide the stiffness of the soil and in the translation and in the rotational axis, about the translation and rotational axis, and that can be provided as a spring support at these locations. So yeah, so these are the spring supports, that point supports that we can provide. Yeah. This the rigid diaphragm part. So we can go to the structure, and in the story tab here, and here when we generate the particular building software, software MIDAS Gen NX itself locates each and every floor, and what's the height of each and every floor, and then assigns the floor diaphragm at each and every floor location. So when I go to the display option here and go to the boundary and then the story diaphragm, okay, and let me undisplay the support. Yeah, so here it's it's the center of mass location that is located by the software, and that is connected to each and every nodes from in that particular level to consider the rigid diaphragm behavior. So here you can see that these blue dots at each and every floor level, they are the center of mass location for each story, and they are connected to each and every node at that particular story to consider the rigid diaphragm behavior. And where we don't want to consider, we can just go to story and we can click on the do not consider, and it will not consider the rigid diaphragm behavior in that particular story. And then we can go on modeling the real-time slab there. If we are not considering the rigid diaphragm, we can just go to the node element, create and create element, and from here we can just go to the plates, select the material, select the thickness of the plate, and define the boundary nodes like this. We can just go and click here, and we can just define the boundary nodes, and it will generate a slab that is having a plate element of thick type, which will consider the in plane and out of plane behavior both. So if we want to consider only the in plane, then we can go for the thin and so on. And with drilling degree of freedom, this is to consider the torsional effect on the plate. So there are different options available here. Now the cracked stiffness part. So that can be considered using the properties tab here, and we can go to the scale factor, section stiffness scale factor, and here these are the different section properties that we have defined. So let me show you that. Sections. This is my edge column, this is my interior column, and this is my beam. These are my beams. So I can just go to the scale factor, and to the beam, if I want to consider 35% of the gross stiffness, so I can just go to IYY 0.35 and IZZ 0.35 and just click on add, and then it will it will add that particular scale factor to consider the cracked stiffness. Similar to that, we can do the same things to the columns. Now, the dynamic properties. So when we are running, this particular example, it can be, it's actually G plus 12. We can go to G plus 20, 30, 40, whatever we want to go to. And when we want to consider the mass. So now we will go to the structure type, and convert self weight into masses. So we will just check on, and this conversion will be in the X, Y, and Z direction. So the self weight will be converted into X, Y, Z direction. And now the next option is when we are applying the vertical loads. So those vertical loads should also be converted to masses. So that can be done in this particular option, loads to masses. And here we can just select the load cases. Like here we have self weight, we already have done in that structure type, live load and SIDL, that these are two vertical loads. So we can apply the scale factor. So that is the 0.5, and for SIDL it is 1. So we can use this particular option to convert the loads into masses, and that will be used to calculate, to create the mass matrix, and then to run the eigenvalue analysis to get different mode shapes. So yeah. And the staged construction, we will be talking about this thing in detail in further slides, so I'm not going into this part right now. Soil structure interaction, so for that I have already shown you, we can go to the boundaries and we can go to define support, point spring, surface spring option. If we have mat foundation, we can go to surface spring option, and then we have mat like plate, we will model that as a plate element. And then we will now we can go to either the distributed spring, or like this, we can just provide the modulus of subgrade reaction of either compression only, linear, or tension only. So it is mostly the compression only type of support which considers the non-linear behavior of the soil, where we have the compressive force on the soil, then only we will have the reaction. Otherwise, if there is any upliftment, it will not show any reaction. We will enter the modulus of subgrade reaction, and then it will provide a distributed spring support for that. So these things can be used to consider the soil structure interaction between the structure and the foundation. And Yeah, so here also, if we have a pile foundation, so in the particular software we have this pile spring support. And for these three kind of soils, sand, soft clay, and stiff clay, the software practically generates the py curve that we usually get from the geotechnical team. So here, using the pile spring support, the software generates the py curve, and that py curve can directly be used as a spring, as a vertical spring and a horizontal spring, to simulate the behavior of the soil, vertical as a linear one and horizontal as a multilinear, which considers the py curve of the soil. Yeah. So these are the different options to consider the soil structure interaction that we can do. Now for the second order p delta effect, so for that we can go to the analysis tab, and here we have this p delta analysis control. And here we can specify what are my vertical loads, the combination of that, and also we can specify the factor. So it will be considering the p delta effect because of the lateral deformation of the structure. So yeah, these are the different parameters that we have to consider at the time of modeling. So let's proceed further. The last thing, the damping and the dampers, I just want to show you how we can provide that. So that is also there in the general link properties, add, and here we can provide that as a viscoelastic damper, gap, hook, hysteretic, laid rubber bearing isolators, and also we can provide the non-linear properties to that particular dampers. So using these options, we can provide that as a spring, in our model to consider the damping behavior. Yeah. So let's proceed further. Yeah, the next thing is how high rise behaves differently from mid rise. So so we have tabulated this particular thing here. So the governing load in the mid rise is the gravity, and gravity loading that is of strength, uh, and that typically governs the member sizing. And in high rise, wind and drift, that is actually a stiffness problem, and that typically governs the high rise structure, the wind and the drift loading. Now related to behavior size, mid rise structure can usually be treated as essentially static, whereas high rise structures are genuinely dynamic. So we are actually dealing with periods, modes, shapes, floor acceleration, and so on. The lateral system is a simple rigid frame is often adequate for mid-rise, whereas high-rise needs cores with outriggers, tubes, or diagrades. We will talk about these different terms in later slides. And yeah, so yeah, the P delta one we have already discussed about this thing. It is usually negligible for mid-rise, and which is that is very much relevant in case of high-rise, and that we have to check at each and every single design iteration. Regarding the serviceability, it rarely governs in mid-rise design. In high-rise, drift and occupant comfort very often govern member sizing before strength does. And the time effects, which is the time-dependent material properties, that is minor in mid-rise, but when we go to the high-rise, the differential column shortening becomes very much critical, and it simply does not exist as a design issue on a mid-rise structure, but in a high-rise it does. Yeah. So if I summarize this thing, I want you to take from this slide, as we go from mid rise to high rise, is from a strength problem to a stiffness problem. So when we are transitioning from mid to rise, the problem changes from strength to stiffness, dynamics, and time problem. And every technique that we are going to talk about in rest of this session that exists because of that particular shift from that strength to the stiffness one. So let's proceed further. Yeah. So what are the different lateral load systems exist, and what are the difference between them? So first one is the rigid frame, which is actually practical for up to 30 stories. So that is nothing but the beams and columns that are moment connected in a rigid, forming a self-contained frame that resists lateral load through bending, not axial wall action. So that resists the lateral load through the bending action, not the axial wall action, and it gives the most open column light floor plate for of any system with no shear walls required, but it is relatively flexible, larger drift under wind or seismic load than wall based systems, and becomes material inefficient beyond roughly 30 stories. The second one is the shear wall or core type of structure. Yeah. So this core can be at the lift location where we are providing the lift in our structure, in our building. So this core can be provided there, and it carries essentially all the lateral loads that behaving like a vertical cantilever fixed at the foundation. It is very stiff and efficient with simple predictable behavior, and the core conveniently doubles as the services like the spine, and the effectiveness drops off. The story that we can go up to using this particular system is up to 40 stories, not more than that. After this, the its effectiveness starts to decrease. The third one is the wall frame dual system that I just showed you in as an example in the model, the dual system, where we have the frames as well as where we have the walls, and when we have a lateral loading, both of them behaves differently. Like the walls, like the shear wall deforms as a cantilever beam where the bending governs, and the frame structure deforms as a shear deformation is there. So when we see the deformation for the shear wall, that is maximum at the location which is very much flexible at the top, the shear wall, but for the for the frame structure, the top one is not that much flexible. So when we combine both of them, so the interaction between these two frames and the shear wall system, that actually helps us or to resist the lateral load system, and then it can go up to the 50 stories. The fourth one is the framed tube. I will show you one example for this particular thing as well. It is nothing but the closely spaced perimeter columns linked by deep spandrel beams from a perforated tube at the building's exterior, and the whole facade acts as a hollow cantilever tube in bending, which is far stiffer than an equivalent weight frame. So interior column becomes optional. Like for this frame tube, the interior columns becomes optional, and this is highly material efficient for its high range. Yeah. The fifth one is the tube in tube, where is a tube structure inside of the tube, and that makes it more efficient. And the maximum height it can go up to the 90 story. And then it comes the outrigger and belt. So where we have a core shear wall in the center, and then the peripheral column. The column is extended at the periphery, and then we are connecting the core to the peripheral column using outrigger, using these beams, deep beams. They are actually they are termed as the outrigger. So they are connecting the cores to the peripheral column. So that is nothing but to increase the base size, to increase the if we say that when we have a higher as we talked about the slenderness ratio in the previous slides, when we have the higher aspect ratio, so that is much more efficient. So that is what we are doing here. When we are going like 100 plus story, we are increasing the aspect ratio like this by providing the shear wall in the center, and then the peripheral column, and connecting them using the outrigger. And this is another example of that, the diagrid, where we don't have columns, we have like these the diagonal members. And then the bundled tube, we can see more a lot of super tall buildings having the bundled tube kind of arrangement, where we have when we go up, the tube system is we are bundling a lot of number of tubes, and then we are making a super tall building. Yeah, so this is nothing but the same that we talked about in the previous slide, but in a format of chart. So the core idea behind every step up this ladder is the lever arm. If we think of the building as a vertical cantilever, its resistance to overturning comes from how far apart the compression and tension elements are. The wider that separation, the more overturning resistance we get from that the same amount of material, because stiffness rises with the square of the lever arm, not linearly. So that is what we see in the outrigger system or the diagrid system, where we are increasing the compression and the tension element, the distance between them, to increase the lever arm. Yeah, that is the core idea behind that. And also, when we have this particular idea, so when we have a discussion with the architect or the client, and they ask us to for 120 stories on a slender footprint, so we already know that we are going to talk about outrigger, diagrid, or bundle tube. We can skip all these particular type of different structures. Yeah. So now let's talk about the wind loading. So what are the different loadings that we have already discussed? Wind load, seismic loads, and other type of loads. So let's start with the wind load, the along wind and across the wind thing. So wind is usually the headline load for the slender tower, and it causes more kind of effect. A pressure pushes on the building. So yeah. So the first part is the along wind response, that is the buffeting caused by the turbulence in the wind direction. In Eurocode terms, is this is captured through the structural factor CSCD, and we will be looking at that CSCD factor, how we can calculate that, and how the software gives us that particular thing. So we will be seeing that in later slides. Yeah. And a crosswind, that is actually the vortex shading, and that is more dangerous phenomenon. As wind flows past a bluff body like a tower, it shades alternating vortices of each side, which creates a sideways oscillating lift force. And when the shedding frequency coincides with one of the building's natural frequency, then the resonance occur. And this is precisely why very slender towers often need wind tunnel testing rather than code formula methods alone. So this across wind is more dangerous than the along wind parameters. And the third one is the occupant comfort, that we have been talking about, like the serviceability criteria and so on, where we check the peak floor acceleration frequently, and then that should not be more than a given criteria. So the peak floor acceleration, that can be checked as a dynamic loading because of the wind. And then how we can mitigate all these things? So we can, by controlling the shape, by the aerodynamic shaping, like a taper, corner cuts, openings, by controlling the shape and by providing the dampers, tune mass dampers, and so on, so we can overcome all these problems because of the wind. So when we see in the Eurocode, Eurocode has defined a lot of criteria for this particular thing. So there are like the difference in the terrain where we are constructing our structure. So terrain category 0, 1, 2, 3, 4. Based on that, there are other factors given, and those factors needs to be considered based on different terrain categories. And then the basic wind speed, and like this VB value. Then we have C direction, C seasonal factors, these factors that needs to be considered. And how these are being considered, we will be seeing that in the software after this particular slide. And these basic wind speed, and then it will be used to calculate the final wind loading, wind pressure. And also there are factors like the orographic effects, the adjacent buildings, the nearby buildings, what is that is causing the effects on the newly constructed building, and the height of the building, how the wind load is changing because of the height of the buildings, and so on. So that needs to be considered based on the Eurocode EN 1991 14 2005. And now the wind force calculation, that is the CSCD that we talked about in the initial slide of this wind loading. So there are three different force factors, which is the external, internal, and friction forces. And the combination of all these forces gives us the final wind force on our structure. So let's see in the software. Yeah, in this particular example, when we go to loads and the wind loads, so here the structure type and the friction coefficient, like the force effects that we talked about in the last slide. So we can use these coefficients. So the orography factor, C naught, C direction, that we saw in calculating the basic wind speed, that we have to enter that here. Seasonal factor and the turbulence factor, building height, all these things that we have to enter those parameters here. Now the orographic effects. To consider the orographic effects, we can go to this particular option, cliffs, either it is cliffs, hills, whatever it is, and the building location, whether it is the upwind or downwind with respect to that orography. And then these are the different parameters like the height of topographic feature, length of upwind and downwind, that we can enter these things. Now the effects of neighboring high-rise structure. So we can consider raising of displacement height. We can consider all these particular different criteria given by the Eurocode, and then we can apply the final wind loading in our structure. And also considering the external and internal pressure coefficient. So the code specifies the formula for external and internal pressure coefficients. Internal pressure coefficient is some factor of the external one, so that we can use using these particular options. Either we can go to automatic, or we can go to the user defined to define those particular coefficients here. And now the structural factor, the last one, CSCD. So if we have already calculated that, we can directly input that particular value here, or we can click on this particular option, and we can, these are the These are the inputs which are directly considered by the software, that based on our modeling, building height, turbulence factor, and all these things. Now we didn't check on these particular orographic and so on. If we consider, it will be considered here. And the along wind natural frequency, along wind breadth, along wind depth, and so on. So for an example, if I enter that as my point 1, so finally it will calculate that structural factor as 1.89, and I can just click on OK, and it will be considered here. So this is how we can consider the CSCD factors to calculate the final force because of the wind loading in the software. So these are the formulas given here in in the Eurocode to calculate those factors. So let's come to the next loading thing, that is the more response spectrum, or the seismic load, we can say, which is the that considers the different mode shapes, time period, and yeah, and that actually depends on the flexibility of the structure. So seismically, tall buildings behave quite differently from short ones, and this slide sets out why. So tall means a long fundamental period, which is T1. That means the simplified lateral force method in seismic codes are calibrated for short period, more regular structures, and they usually become invalid or at least unreliable once our period gets long and our mode shapes get complex, which is essentially always true for a genuine high rise. So for an example, if we have this particular response spectrum curve and we have a very high period of a building, like when we have a high rise structure, the period increases, and that comes somewhere here. So that means our base shear, the force that is for which we are going to design the earthquake force, that lies somewhat here. So that is not the actual force that is going to be there in high rise structure, but because of the high period, that tells us something like this. So we cannot rely on the fundamental mode thing or the equivalent seismic method for the high rise structure. We have to go for the response spectrum, where we consider number of modes to get the 90% mass participation, and then we combine the results of those modes using either CQC method or SRSS method to get the final result. And also when we have a very high rise building, so the force thing, that the force value actually decreases, but the ductility factor increases. So the Eurocode defines the mid or the DCM or DCL or DCH terms in Eurocode, that is actually for low, medium, or high ductility. So that sets the behavior factor which is a lot which we use to consider the which trades off the design force against detailing requirement. So basically, when we are going for the high ductility, what we are going to do is we are designing it for lower force, but we are considering very high ductility, and we have to provide a very good detailing to consider that high ductility part. And a higher ductility class lets us design for a lower force, but demands much more careful detailing to actually deliver that ductile behavior in reality. So there are different fact like ductility classes given in the Eurocode to consider. Yeah. So if I summarize this thing, when we are going for the high rise structure, we should not be going for the single mode analysis, which is the equivalent static method. We have to go for the response spectrum analysis method, where we consider number of mode shapes. And also there is a non-linear analysis, which is the push over analysis, that also can be considered to get the final displacement, where we get the base shear versus displacement curve. So what is our final displacement, and so on. And when the hinges are being formed, so that also we can see in the software, when the hinges are forming based on the backbone curve given by Eurocode, or we can generate the backbone curve using the in the software using GSD. So we will see that later on. Regarding the response spectrum curves, Eurocode allows us to gives us two types of response spectrum, which is the type 1 and type 2. So type 1 is generally, if I say in simple terms, it is for higher magnitude earthquake, and type 2 is for the lower magnitude earthquake. So in the software, we can directly go to the Eurocode 8, and whether it is horizontal, vertical, whatever design a spectrum, and there we can select the type 1 or type 2, and that can be considered accordingly. And also we can set the behavior factor q, so based on that the spectral data will be calculated and the response spectrum curve will be generated, that is given in the Eurocode, and then we can consider that particular loading to perform the response spectrum analysis. Yeah, so that use so the two major loads, wind load and the response spectrum loading that we have talked about. The third one is the time dependent loading. That is actually very much critical in case of the high rise structure. So what are the different time dependent material properties? So first thing is the concrete strength, which is the characteristic strength of the concrete, that is actually the strength increases as the time goes on. And then the creep, so that is nothing but a sustained stress which is slow, ongoing, and it keeps on increasing. There are then it has two effects. One is linear, another is non-linear, which when we remove the load, some part of that creep is restored and some part of that is not restored. So yeah. And then the third one is the shrinkage, which is because of the loss of the moisture in the concrete, so that shrinkage happens. So the chart on this particular slide, like this particular curve here, shows the behavior of the creep and also the shrinkage. So we can notice that the curve rise steeply in the first initial days and then flatten. So most of the movement happens early, but not all. It is the most, but not all. And the tail matters for very tall towers with long service lives. So as we go on, the most of the things are happening here, it is steeply increasing and then it flattens out. So for the high rise structure, when we go, so this particular region that we also need to consider, at the time of analysis. So let's see first the response spectrum and the time dependent material things here in the software, and then we will proceed further. So here we can define those things by going to properties and creep, shrinkage, add. Yeah, so there are different parameters. So we go to the European code, and then we have to specify the characteristic compressive cylindrical strength of concrete at the age of 28 days. So suppose I am going for the 50,000 kilonewton per meter square, relative humidity 70%, notional size of the member, which is the H value, that is the 2 times of the section area upon perimeter in contact with atmosphere. So we will first write it as to start the calculation, we will write a random value. Then the software calculates on its own notional size of each and every member. It's not possible to calculate everything and write it manually. So the software does it for us. So we will go for the EN 1992 type of code. Age of concrete at the beginning of shrinkage is 3. Then we go click on the show result. So the creep coefficient, which we have already seen in the slides, and this is the shrinkage strain. So these are the values for that, and these are the values for creep coefficients. Yeah. And when we want to define the compressive strength, we can go to the compressive strength, modify. So here the code Eurocode, and again here the mean compressive strength of concrete at the age of 28 days, and also we have to consider the delta F. So that is the 8 MPa based on Eurocode. So when we are considering 30 MPa, so it will be going to 38 MPa for while defining the parameters for the compressive strength and the type of cement. Yeah. And then we link, so we link these material properties with the defined grade. So we have already defined this particular grade C3037, and in that we are linking the creep shrinkage and compressive strength material properties that we just defined as a time dependent material properties. And also the thing that I told you, the notional size, so that is what we can do by going to change properties, and the parameter given based on Eurocode and CBFIP is the same, so we can use directly CBFIP. And if I click on this three dot button, so here you can see that the H value for each and every elements are calculated by the software. Yeah, so we don't need to worry about that particular part. The second part is the response spectrum loading. So that can be applied by going to load and the dynamic loads. There we have response spectrum as well as time history loading. We are not going to time history load right now. So response spectrum function, modify design a spectrum. And here we can select the respective code. Yeah. And then there are four options. One thing is the horizontal elastic, vertical elastic, horizontal design, vertical design spectrum. I'm going to horizontal design spectrum. Ground type, these are the different ground types given in Eurocode. And then the type 1, type 2 that I told you earlier. These are different types. We have to select that. And then the peak ground acceleration, importance factor, behavior factor Q, and the lower bound factor B maximum up to which we want to see the results. So based on that, we can define the response spectrum curve. Now, when we have defined the response spectrum function, we go to the load cases. And here in this particular load case, we will select which plane we are applying the response spectrum loading, which is the XY plane. And excitation angle is 0. When we have a symmetric building like this, we can directly enter that as 0. And then the modal combination control, which is based on CQC or SRSS or absolute or linear combination, whichever we want to combine the modes, we can combine them in any way, and then we can assign that. Now we have one more option here, that is the that is termed as auto search angle. When we don't have the plan like this, the orthogonal plan, we have some unrealistic plan, which is the not symmetric kind of plan. So then we don't know what is our principal axis or what is our principal angle. So in that case, we can't directly apply the loading at 0 degree. So we have this particular option, that is the major auto search principal angle and then major. Then we apply the loading by considering the major in X, and in Y we apply the loading by going to the ortho. So what the software does, it applies the loading along this particular periphery at each 1 degree interval, and whichever angle, like the 30, 45, 35, whatever angle is giving us the maximum result, that is stored here. And then that is the RSX, and then RSY automatically takes the 90 degree of that particular angle, the orthogonal axis. First, it finds out the principal axis, which is causing the worst effect on the structure, and then it applies the another loading at 90 degree of that principal axis. So we have these options to apply the response spectrum loading. Yeah. Let's go back to our slide. So yeah, now let's talk about the construction sequence, construction stage. So we all know that the buildings are not constructed in one single day, and especially if it is a high-rise structure, then it is going to take a lot of time, like 2 years or sometimes 3 years, something like that. So when we have the time difference between the construction of elements, like the bottom floor and the top floor, so the creep, shrinkage, compressive strengths are also going to be different for those parts, the bottom and the top part. And then we cannot simply model a single model like this. We cannot just simply sorry yeah, we cannot just simply all the floor at once apply the loading, dead load, live load, wind load, earthquake load, run the analysis, and then take the results of each and every elements and design it for that. We cannot do that, because in that case we are ignoring the effect of the time dependent material properties. That is very much crucial when the time of construction is very high, and also the construction sequence, like when the boundary conditions are changing. So we have to consider all those parts, especially for a high rise structure. So in that case, what we need to do is we have to model it as a single step by step, the first floor, then the second floor, and similarly we go to the last floor, whatever floor numbers we have, and then we apply the final loads. Like we apply the final loads like this, live load, wind load, earthquake load, something like that, and then we check for the results of each and every construction sequence. So what I want to say here is, when we are going for the very final model and check for the bottom story results, so and for using the construction stage, and for a model where we are not using the construction stage and we are checking the results for the bottom story, the demands are going to be different. So the sagging moment, the hogging moment, the shear forces are going to be very different in both of the sequence, because we are considering here the time dependent material properties, and in that part we are not considering those time dependent material properties. And yeah, and also the boundary conditions, sometimes we provide temporary boundary supports that changes the behavior of the beam from cantilever to simply supported or propped cantilever, and in the end that changes to the fixed beam. But during the construction process, the boundary conditions also changes, so we have to consider those change during the construction process. That is why we need this particular sequential construction or construction stage. So for an example, it's our conventional analysis, where what we do is we model the whole structure at once, we apply the loadings, and then we sum up like, yeah. So we have this particular structure. So this is my model where I have modeled all of them at once, and my first story is loaded, my second story is loaded, and then we are summing simple linear superposition of these two different scenarios, and we are getting the final model here. So this is what we do in the conventional analysis. In construction stage analysis, we only model one single floor. That is actually the practical scenario. That is actually the practical thing that is happening at the site. And then we model the second floor after that. And then we are specifying the loads. So in the previous case, we have all the sets active in our model, and then we are applying the loads one by one and each floor. But if you see this particular beam, it is being shared by these two columns. So so if we say like the stiffness of the columns and if stiffness of the whole structure is different from the first stage to the second stage. So here in this particular conventional analysis, it remains the same for these two situations. But in the case of construction stage analysis, it changes. So we have only these two columns and one single beam, and then we have the whole structure. So that is very much crucial to get the final result, and because of this the final result changes a lot. So it's for the example purpose, when we go for the conventional analysis, you can see that the results here, the bending moment in the column is 16.6 and the saggy moment in the beam is 29.2. But when we go using the construction stage analysis, that changes to 35.3 and 32.3. So when we go for this conventional analysis, we end up designing for these magnitudes. Ideally we should not be doing that, because the after the whole construction sequence, we are going to get the higher forces than this particular force. So we need to consider those additional forces. Now let me show you what are the things available for this in the software. So this is when I turn off the 3D view. This is the building having shear wall and the frames. So when I go to the construction stage, define CS and add and modify. So here we have three options: element, boundary, and load. So and the duration. So duration means what is the time that this particular construction stage take to finish. So suppose I am constructing the first floor right now. So how long will it take to finish the first floor construction? So that duration we have to enter that here. And then what are the elements already exist when we are constructing this particular thing? So we already have, suppose, the foundation. Then we are going for the first floor. So we will activate the foundation, which will have some maturity. Suppose we want to consider 7 days of the maturity or 28 days for that particular already activated element. So we can activate that here. And then the boundary conditions. So when we are constructing the first floor, our foundation is already there, and that is having some spring support or some fixed support or different type of supports can be there. So we can specify those boundary conditions here in this particular construction sequence, and what are the different loads that is there in this particular construction sequence, CS01. So we define these three parameters, and then when we go to CS02, now those CS01 elements effects are being carried forward to CS02, and then we are going for the third floor construction. So then again, if we activate the elements of the first floor that has already been constructed. Then we go to the boundary conditions if there are any change, and then if there are any additional loads are applied, then we apply those additional loads here. And if we are, suppose, deactivating some loads or deactivating some boundary conditions, so we already have applied some boundary conditions. Now in the further stages, we are removing some trussels, some temporary supports. So then we can go to deactivate option, and then we can deactivate those boundaries and the loads as well. If you are applying some loads here, we can deactivate them. So first we need to go to make groups. We go to group option here, and then we group all those elements. Those are going to be constructed at the same time so that we can activate them at once. So this is the structure group. And then we also make group for the boundary conditions. What are the different boundary conditions? And then for the loads, what are the different loads that we are going to apply? So these are the groups that we define here, and then we activate those groups during different construction stages to consider that accordingly. Yeah, and this is the mini construction stage, you can say, which is used. Suppose we have 7 days, and I want to divide this 7 day in further days, like 1, 2, 3, 4, 5, 6 days. Then we can use this additional step option, and then we can specify additional loadings in this additional steps. We can go to loads right now. Here only the first and the last. First means start of this construction stage, and last means the last of the 7th day. So that is there. But if we add something like one here, and we will get another option in between first and last. We can specify any loading there if we are adding some loading or something like that. Yeah. So these are the inputs of the construction stage that we define. And the time duration, like the thing in the time dependent material properties that I told you earlier, where we consider the effect because of the time change. So that is being considered based on this duration. So you can see that the first construction says taking 7 days, then 14, then 21. So similarly, we can go on. And the last one, if we want to check the effect after 10 years or 20 years, so we can accordingly enter the number of days. We can accordingly like enter 10,000 number of days. So we can check the result of this particular structure after 10,000 days, how much deformation is going to be there, what are the forces that is going to be generated after a long period. So that can be checked here. Yeah. And yeah, this is the broad way of defining construction stage. We also have one wizard option to you can say quickly generate the construction sequence if when we do not have a lot of changes in the loading and so on. So we can use this particular construction stage wizard as well, where we specify yeah, the number, these are the different stories and all. And then we can just go automatic generation, and we can specify what are the load cases, how the story is going to be incremented one by one or two stories at the same time, and how much time this story is taking to construct, and what is the member age. So the members, those are already activated in that particular story, what is the maturity of that. So we can use this shortcut method, and then it generates the construction stage quickly. So if I show you one by one, so this is my CS1, this is my first floor, this is my first floor, and now this is CS2, second, third. So progressively this particular structure is being constructed. And when we check the result without construction stage and with construction stage, so that actually changes a lot. So let me show you. I have one example to show. So I go to the post processing mode, and I go to the last construction stage, and I will go to results, poses, beam diagrams, and then summation that will include the effect of creep and shrinkage and dead loads and other live loads and SIDL if those are there. Legend apply. Okay, so these are my maximum moments, that is 157 and minus 318 sagging and hogging. And I have another model that I just took out from that same model, and I deleted the construction stage. And here we don't have the effects of the creep and shrinkage because we haven't defined any time dependent material properties. So when you check because of the sulfate only, so it is 37 and 68. Although there are live loads and SIDL, but we can delete those effects. Still, that's very high in the case of construction stage. The results are very, very high. So we have to consider the effect of construction stage. Yeah. So let's go to the slide. Moving forward. So we have understood what are the time dependent metal properties, what are the construction stage sequence. Now we will be talking about what is this column shortening and why does this happen. Yeah. So this particular column shortening is nothing but the differential settlement of the vertical elements like the core walls, the columns, those are there. So that actually happens because of the creep, shrinkage, elastic. So there are basically inelastic deformation or elastic deformation. So elastic deformation is something that immediately happens and then it is restored. But the inelastic one, that is because of the creep and shrinkage, so that is not restored, and then there is a permanent deformation. So that we have to account. So when we go for like 30 stories, 40 stories, or more than 50 meters building, so the loads on the vertical elements keeps on increasing, and the creep and shrinkage effects keeps on increasing, and we have to consider those effects because then there that causes if like let me go to the further slide. So here you can see that when we have a central column here and then we have the edge column, so this particular column here, it is having this much tributary area of the slab, and the loading is being applied to this particular column as single p value. And this column, the edge column here, it is having these two slab area and the loading is 2p, and this central column is having the loading of 4p. So since the loading changes, if now we are talking about the same cross section of the same cross section columns, that also depends on the stiffness and all. So right now when the loading changes, so the deformation, which is you can see here, like when we apply a p value, then there is a deformation as delta L, which is nothing but PL upon AE. So then the central column will have much more deformation than the peripheral column. So when the story height increases, this value becomes so much significant that the deformation is so much significant that the slab which is connecting all these columns and beams, that tilts and that bends at that particular location where we have more deformation, and that is where the serviceability criteria governs. So we have to consider that why this particular column shortening things is happening and what we can do to mitigate this particular thing that we are going to talk about in further slides. And that causes the additional forces in beams and slabs. Yeah. So for steel structure, it mostly remains on the linear side. So the shrinkage part is not there, but yes, the creep part is there. But steel structure takes the elastic deformation is much more than the inelastic deformation. But here in the concrete structure, the inelastic deformation is more than the elastic deformation. So for the elastic shortening, the after removal of the load, that is restored, so that is nothing to worry. But for the inelastic one, that is because of the creep and the shrinkage, so we have the more deformation, and then the column deforms permanently, and then we have to consider that permanent deformation, why it is happening. And then we have to, at the time of casting of that particular column, we have to assign this particular deformed value. So this is nothing but the summation of elastic, creep, and shrinkage deformation. So yeah, so what is actually happening is so it accumulates over height. Even a small amount per floor, a few millimeters, if I say, multiplied by 50 to 100 floors, adds up to tens of millimeters of differential movement by the by the top of the building. So a magnitude that would be structurally irrelevant on a 5-story building becomes a serious serviceability and even safety issue on a 60-story tower. So yeah, so core versus column. So if I say about this particular thing is core and there are the columns, so the core typically has a large cross-sectional area carrying relatively low average stress, while peripheral columns often carry high stress on a smaller section. So because shortening is fundamentally stress dependent for the elastic and creep components, these two element types shorten by different amounts. And since they are both supporting the same slab at each floor, that difference tilts every slab in the building, floor by floor after floor. And the real consequences read like a punch list from a defects report. So if I list them out: sloping floors that are noticeable to occupants and that fail flatness tolerances, cracked partitions as the structure moves beneath fixed, brittle finishes, facade and curtain wall distress as movement accumulates unevenly across the building envelope, overstressed slabs and beam column connections carrying additional bending moment they were never designed for under conventional analysis. So, and misaligned lifts and MEP risers. So these are the different scenarios generate when we do not consider the differential settlement between the columns. Yeah. So let's see that what are the other effects, the effects that I just mentioned. So in this particular option, so that I just said that the slabs may not be truly horizontal after some time. Beams could be subjected to higher bending moments. The load transfer mechanism, the path of the load transfer that disrupts, and then there are the non-structural effects where the cracks in the partition walls happens, inclination in the pipelines, deformation of vertical systems, and these are the different scenarios occur if we do not consider the column shortening analysis. Yeah. So what are the compensations? Like what should we do when this particular column shortening thing is happening? So so depending on the construction material, when we if we use the reinforced concrete structure, so the pre-slab installation shortening does not really have much importance, because why is it so? When there is a shortening in the column, when there is a deformation in the column, vertically deformation, so when what we can do is at the time of casting the slab, we can set our formwork in such a way that whatever be the deformed value, we can provide the formwork at that particular height, so that after deformation, that comes to the leveled value. So that comes to the level so that the slab does not dip. So pre-slab installation thing is not of much importance in case of RC. We can compensate it by leveling the forms, and but the post slab installation, when we have casted the slab and then we are constructing the stories above that particular story, so then the column again starts to deform. There is a differential deformation among the columns, so that needs to be considered. And before casting that, we have to perform the column shortening analysis, and we have to check what is the additional deformation happening at each and every column, and based on that we have to provide that particular formwork height. We have to set that particular formwork height so that after deformation that reaches to this point number 2, which is this is my height of the column where we are casting it, and then after particular deformation we want it to be reaching at the same level. Whereas for the steel structure, the columns are fabricated to exact length. So this pre-slab installation thing comes into picture in this steel structure. We have to consider that a pre-slab installation, because the columns are fabricated. It is not casted at site. Yeah. And needs to be known, and compensation for the summation of pre-installation and post-installation shortening. So we have to compensate it for both pre and post shortenings effect. And for the RC structure, we have to consider the post-slab installation. So when I go back to the model, yeah, here, when we have run the analysis, so in that particular thing, we have here an option that is column shortening graph for construction stage. So in this particular column shortening graph for construction stage, so what we can do is we can just go and select a particular column like this. Yeah. So here, when we go to the add new, we can provide we can provide some name, we can provide the coordinates, and then there are, you can see that there are different options: elastic plus up to casting, elastic plus sub level to casting, and elastic of total. So elastic plus up to casting means when it will consider the deformation, elastic deformation up to the casting level. So when we suppose we are working for the third floor, so up to the third floor, whatever be the elastic deformation that is being considered when we choose this particular option. So when we go on constructing fourth, fifth, sixth floor, so then the effect of those ongoing the effect of those floors that is above that considered floor, that will be considered. Because of that, what is the elastic deformation? And then total means it is the summation of these up to and sub to casting. So this elastic deformation, then creep, then shrinkage, and then total. So we are basically considering these three parameters to consider the column shortening effect. So here, yeah, and then at which construction stage I want to check my particular thing. So if I go to the very last construction stage, and then I will just go for these functions that has already been created, and story or height, apply. So it generates a curve like this. So here you can see that yeah, test this blue line is for creep, this orange line is the elastic deformation, and the green line is the shrinkage one, and the total one is the summation of all these three. So we can say that at each height, these are the different story levels and how it is changing for the last construction stage. What is the maximum deformation for this particular column at the very top? So this is something less than 7 mm. So this is what happening because at the very last construction stage. So we do get this graphical result because of the creep, elastic, and shrinkage, and we need this final value for this. So this value is given to the contractor or to the construction to the worker at site, and then they set the formwork such that after providing the formwork at this particular height, so it will have that much deformation, and then the whole level will be at one single there will not be differential dip, and the slab will not be going to deform differentially. So suppose if I go for the construction stage number 9, so this is how it changes like this. Yeah. And also here, what are the different things that we have considered? So we have considered eigenvalue analysis having 15 number of modes. So we have different options like subspace, iteration, Langos, rids. So when we have the higher number of modes to be considered, we can go to subspace, and if we have lower structure, we can go to Langos. And if we want to consider only those modes which have the significant mass participation, we can go to the rids vectors. Yeah. And we have performed the construction stage analysis, and let's go and check for the results. So we can go and create the load combination, auto generate, and the Eurocode. Yeah, let me read it. RSX, RSY, and also the orthogonal effect because of the that auto grouping. So here the when 100% of the earthquake loading is being applied in X direction, then 30% will be applied in the other direction. So that 130 rule is being applied here. Okay. So these are the load combinations generated, strength and serviceability based on Eurocode. We can just go and perform, like we can check for the deformations, forces, stresses. Let's go and check for the value for how the dead load value is changing, because the moment value is changing at each and every construction stage. Yeah. And this is 28 minus 44. Then we are going to CS2, 29, 43. Then again, slightly change. So because of the dead load, it is slightly, you can see that in the legend tab, it is slightly changing the maximum and minimum value as we are keep on adding the floors. Yeah. And here in the construction stage, we don't go for check for each and individual results. We go for the checking for the summation that includes the time dependent material properties effect. So yeah, TS1, 02. So this is how we can check for the results in every construction stage. And we can also go to the story table, and then we can check for the drift, which is very much essential for the high rise structure. So for the euro, we can check for the country code. So right now we will go for NTC 2018, so that uses the same parameters based on Eurocode, and we can go for story drift value. So that is wind, earthquake, equivalent static, and the response spectrum. We can go for that. And the vertical combination for self weight live load, I'm going to use the factor as 0.25. This is to consider whether the P delta will be considered or not. So what is the maximum story drift, and what's the maximum drift of all vertical elements? So this is modified drift, story drift, and this is story drift happening at center of mass location, which is calculated based on the rigid diaphragm that we have provided. Drift in X, drift in Y, and then combined drift. We can then go and check for story shear force ratio. So let us go for the Y component of the force, and we will go to the bottom. So here you can see that the top floor the top floor frame is governing, which is the frame, which is the having 3200 kilonewton of force, and the wall is having this much force here. So the maximum is having because of the frame for the top floors and the walls. And as we go to the down, we go to the bottom. So here the again the frame, the distribution between the frame, the force distribution between the frame element and the wall elements can be checked here. And yeah, so here this is the frame, and this particular story, the wall is not taking anything. Here you can see that this much force is taken by the frame and this much is by the wall. So we can also check what is the contribution of the frame, what is the contribution of the wall, that is taking the load, the lateral load resisting system, how much loads they are distributing among each other. And also we can go and check for all these different results: overturning moment, weight irregularity, and so on. Yeah. So, I will show you one example of the outrigger and the bundled the tube system, the tube structure. So I have one example for that. So here, if I turn on the 3D view, this is my core, the shear wall, and these are my closely spaced columns. So here, as you can see, these are so arranged like it looks like a tube. There are very less area for the windows and so on. So that's what the tube structure is for. And here again we have performed the eigenvalue analysis, and the supports, we have provided the fixed support. We have provided the fixed support, and the loadings have been applied in similar fashion that I just showed you earlier. So the total height of this particular building is query nodes. And I go from this to this. So it is 163 meters high, tall building. Yeah. So this is how the this is the equivalent static loads that has been applied, the seismic loading, which is actually not the correct thing to be done for the tall buildings, but just for the sake of example, I am showing that to you. We should ideally be going for response spectrum analysis. This thing here, the response spectrum, we should be doing that, and then we can check for the mode shapes results, and we can go to mode shape, vibration mode shape, and then we have considered a total of 50 mode shapes here. Legend, contour, apply. So that is our first mode. Then we go to the second mode, third, fourth mode, which is twisting mode. The third mode is the twisting mode, where we have the rotation. When I go to the top view, this is our third mode. So we can go to this. Here you can see the time period for each and every modes. We can now go to this table that actually lists down the frequency, the period for each and every modes, and the mass participation ratio for each and every mode. So the first mode is in the y direction, that is governed in the y direction, which is 70% most mode participation ratio. The second mode is in the x direction, which is again the same. And the third mode is in the rotation, about the rotation z, which is having the 80% of mass participation ratio. Yeah. So these are the different mode shapes that we can check for the tall buildings. And again, the story things that I have already shown you, that those things are being checked. What are the ratio that is governed by the frame and that is governed by the core. And again, I have one more example to show you. Yeah, let me cancel this one. I will open that particular example. to show you the outrigger system in case of the tall buildings, how they are being modeled, how the construction stages have been defined in different different structural system. Okay, so let's go back to this PPT. And I would also like to show you one more thing regarding the non-linearity, which is the pushover analysis that I told you about. So here in the pushover tab, in the pushover tab, we can just go to the load cases, global control first, where we set whether we want to consider the effects of the permanent loads before performing the pushover analysis that we want to define here. I will just set one value and then the pushover load case add. So we can specify pushover load cases in different ways, which is one is the static load case, uniform acceleration, mode shape, normalized mode shape. Yeah, so these are the different 4 ways of applying those pushover loads. So we can divide that loading into number of steps, either 20, 50 or 100, and we will consider the P delta effect along with that. And if we want to consider the effect of the earlier applied permanent loads before performing the pushover analysis, we can consider those effects as well using these particular options. And these are the different incremental methods. So we generally go for the displacement control, where we specify the master node. Suppose this is my top node, and I'm giving that 100 mm of deformation for this particular node in X direction and add. So the load will be applied. I'm applying the EQ. So the load will be applied based on this particular loading, whatever we have defined here in EQX, and that will be divided into 50 number of steps until and unless we get this 100 mm deformation. And then the curve, the base shear versus displacement curve will be generated. The pushover curve will be generated. So it also asks for the hinge properties. We can go to the hinge properties here, and we can specify the moment rotation, moment curvature, distributed or lumped, and whether like the properties here, the linear, bilinear type of curves if you want to consider. And also if we want to go for the skeleton or fiber model, so we can define the fiber hinge properties as well as the skeleton model and perform the pushover analysis for that particular hinge. Here we can go and define the backbone curve based on this particular given diagram. So these are the non-linear options that can also be used along with the tall building. Now let me see. Yeah, that is here. So it's an example of that outrigger system. So there are a lot of construction stages you can see here. So we go to the first one, that is nothing but the foundation, and then the walls are being constructed, then the peripheral column. I'm just changing the construction sequence here. Sequentially, these walls are being generated. Yeah. So let me show you that. Yeah. So here, this system, you can see that these are my uh, peripheral columns, and then we are connecting the central core with the peripheral column using these beams. So these are termed as the outrigger system. So this is one of the very huge, which is actually the prototype of the low table tower Korea. So that I am showing you here right now. So here you can see that these are my peripheries and these are the central core. And here you can see the construction stage has been arranged in such a way that after 1 year, 3 year, 5 year, 10 year, 30 year, and after 50 years, what are the effects going to be there? So those things we can check on. I will go back to my PPT. Yeah. So with this, we have covered the difference between the high-rise and low-rise structures. What are the main loadings? What are the main things that we need to consider for that? The seismic, the wind load, the time-dependent material properties, column shortening, construction stages, how we can define those stages, and how we can consider the duration of the construction stage, and what are the effects of column shortening that we have discussed so far. So with this, I would like to summarize my presentation here, and what we need to consider, what we need to remember is the high rise is a stiffness, dynamics, and time problem, not just a strength problem. And wind is usually the governing lateral action, and wherever seismic loads are relevant, we can apply it there. And the lateral system scales with height. So we have seen that frame to core to dual to tube, and then goes to the bundled tube. And regarding the modeling, we have to consider those modeling things very, very, very carefully, where we need to consider the cracked stiffness, construction stage, P delta, dynamics, and soil. So if we do not consider that, the answer can lead, it can lead to a wrong answer. And then the column shortening, which is unavoidable. And we have to analyze it, compensate, so that the slabs tilt and those things will not take place. Regarding the design part, I hope that in the previous sessions, the design of the foundation and the beam and the column designs have been covered. So I'm not practically covering those parts here, because the steps and all remains the same that we have already discussed in the previous sessions. So with this, I would like to conclude my session. So now I will open the, I would like to discuss question and answers. If you guys have any question and answers, I would like to discuss those question and answers. Yeah, I will go
Yes,
to
sir.
the,
The attendees had sent some questions. I'll upload them to the question box.
yes, yes, thank you.
I have sent them, sir. Hope you can see them.
Okay. Uh, Let me read that. Can we design, the first question is, can we design a high-rise building without a transfer floor? In Sri Lanka, many of high-rise buildings have transfer beams, not transfer plate. What are the occasions that transfer flows are taken into consideration? If our high-rise structure is unsymmetrical, how we mitigate the torsion effect using shear walls? Why should we do P-delta analysis? What it checks? Okay. So regarding the, can we design a high-rise building without a transfer floor? So transfer floor is actually the floor that provides us the alternate path, like the load path, that where we can go to. The load path is actually being changed from between the floors above and floor below floors. So can we design a high-rise building without a transfer floor? I need to check that part, if how we can handle this particular thing. And as you mentioned that in Sri Lanka, many of high-rise buildings have transfer beams, not transfer plate. Okay, what are the occasions that transfer flows are taken into considerations? So what do you basically mean by the transfer beams, not transfer plates? So you mean by like there are no transfer plate mean transfer slab?
Yes, sir.
Okay, can you confirm? Okay, okay. Uh,
No transfer plate. Most of them are transfer beams.
okay. Okay, this actually requires me to check for the Sri Lanka national annex or something like that. How we, what is the criteria that is being followed there. So I will first review this thing, then we will answer it via the mail to you. How should we consider that or not? Okay. If our high-rise structure is unsymmetrical, how we mitigate the torsion effect using shear walls? Okay, for the torsion effect part, that is why we are going for different types of the high-rise structures. Like I have talked about the bundled, I have talked about the outrigger or the diagrid, or different types of the tube system. So they are actually the principle is same. We are keeping the peripheral column as far as possible to the core, so that the lever arm increases, and that the arrangement should be like that. The columns should be provided in such a way there should not be torsional effects. So we need to check for different types of the configuration of the high rise structure. So there might be because of the unsymmetry, there might be the torsional effect. There is no question in that, but we have to arrange our structural configuration in such a way that those things should be mitigated. And when we are finalizing a single type of configuration, we need to analyze that, and we need to check whether there is a the mode shape. When we perform the mode shape, where the first mode must never be a torsion in rotation. So we need to check that part. So accordingly, we need to shift our like the core and the peripheral column. So we that needs the iteration actually. And why should we do P delta analysis? What it checks? So basically, P delta analysis is when we have any structure. If we take an example of a column, a cantilever column, and which is fixed at the bottom, and then we are applying lateral force on top of it. Suppose 1 kilonewton, and then there is a deformation, and then we are applying 1 kilonewton load from the top in vertically downward direction. So one load in the lateral direction, one load in the vertically downward direction. So because of there will be a deformation because of lateral 1 kilonewton load, suppose 10 mm or 20 mm. So initially, because of that vertical load, there was not any moment or something like that. There was only the compressive axial force. But because of the deformation of the lateral load, that vertical downward loading is causing an additional moment. So we should be considering that in the case of high-rise structures as well. That is just a simple example where because of the lateral loading, wind load, seismic load, it is going to sway. The building is going to sway, and then there is going to be the secondary moment or secondary forces because of that vertical loading, the self weight, the live load, the imposed load. So that is causing the additional bending moments in our structure. So we need to take care of those parts as well. Regarding the first and second point, I will see, and we will answer that later on. Regarding the third and fourth, I hope that I answered that. Okay, let's go to the second question, which is from Sahan Hasantha. Does MIDAS have any option to analyze the load for tuned or isolated dampers of high-rise buildings due to seismic vibration and earthquakes? Uh, okay, I think I have shown that particular uh, option during the presentation. Let me show you. So we can model those dampers using this particular general link option here. And there are different types. First is the element type, where we have the only spring and linear dashpot. Then we go to the force type, and here we can define that dampers using the viscoelastic gap, hook, hysteretic system, and so on. So based on tune mass dampers or whatever we are using, so we can define those sorry sorry, we can define those properties by using these particular options. Like if I go to the viscoelastic damper and I go to properties and I define these different parameters: reference velocity, damping exponent, bracing stiffness, damping force, and so on. So using these, if for an example, if I show you one thing, one test, and I just take some random values here as well. Okay. And then we can, suppose I want to specify that here, suppose I'm going to apply that as a diagonal one. So I can go to the general link, test, and just provide that as a spring. So this is how we can provide that viscoelastic damper or different dampers as a spring. Here you can see that a spring and a yeah, damping dashpot kind of thing has been generated. So let me go back. So when we model that and assign that in our model, so when we perform the analysis, so the force distributions and the loadings and everything do consider those dampers accordingly. So I hope you are asking this particular thing: does MIDAS have any option to analyze the load for tuned or isolated dampers? Yeah. Going to the next one. How to deal with shrinkage effect of the rigid structures in case of shear wall structure with wall and slab monolithically casted. So can you please elaborate this thing? What do you mean by the shrinkage effect? Like what's the problem you are mentioning here? If we want to consider a simple shrinkage because of the casting, that we can consider that, and the change as well by using the construction stage sequences. And here we are mentioning that how to deal with shrinkage effect of the rigid structure in case of shear wall structure with wall and slab monolithically casted. So like if you are saying that when we have two different grades of the slab and the wall, and whether there is going to be a differential shrinkage since the grades of the concrete are different. So yes, that can be considered in the model by defining different grades of the slab and the wall, and then defining two different properties to those two different grades. So that can, I think that you are asking for that part, and let me know if there is something else. So we can just go to creep shrinkage and we can generate two different properties. One is C3037, another is we can go for defining yeah. We can go for defining suppose C50. So we have two different properties, and then when we have a like beam and the column, and we have two different grades, so what we can do is I'm going to define one more grade here. Concrete 50, 60. So when we at the time of material link, we will find it here two options. So we'll just go C3037 has been assigned to this. We will assign C and S to this particular one. So we have two different grades having two different creep and shrinkage properties, and accordingly when we run the analysis, it will be considered in the software. Let me know if there is something else you want to answer. There is something else in this particular question that I haven't answered. Mr. Prageet Nalaka. And yeah. Okay. The next is the what are the parameters need to be considered to model on sloping ground consideration. Okay, okay. So when we are, this is from Ravi Kant, when we are going to model that in the sloping ground, so as far as I understand that we suppose we are providing the column height changes, the column height, or we are providing the foundation like the pile foundation, the height of the piles changes, the depth of the pile changes. So we have to model that different length of the piles in that particular model along with the superstructure, and then we have to provide the boundary condition as it changes along the slope, uh, yeah, around that particular pile foundation. So those boundary conditions that I have already explained using the point spring or the pile spring option, where we specify the soil behavior either as linear, compression only, tension only, or multilinear, where we specify the force deformation function. So the first step is we get it done from the geotechnical department, where like the stability point of view for that sloping ground. And when it is done, they will provide us the PY curve or the stiffness of the soil, so that we can provide using these different options, the stiffness in the compression only, or in the multilinear option we can directly provide the PY curve that we get from the geotechnical department, and then we assign that to the different depths of the pile foundation. So that can consider the soil, that is actually the soil structure interaction. And the if you are like concerned about the stability of the structure on that particular sloping ground, so first the stability needs to be ensured from by the geotechnical team for that particular slope, and then we will get the stiffness of the soil, and then we will provide that in the software and perform the analysis. Okay. So again from Mr. Ravikant, how to model building on sloping ground. So the modeling process remains the same. Either it is sloping ground or the plain ground. The modeling is process going to be same. So we are dealing with the FEM software. So we will be modeling that like we have the coordinates of each and every column. We have the coordinates. We have the location of each and every slab. So accordingly, we will create the column locations. We will provide the slabs and so on. Only the thing that will change is the height of the foundation that we are providing there, either if it is a isolating one or the pile or the mat with piles. So those depths are going to change. So we have to model those depths, like if for an example, if I show you, so we can just go to the node element, extrude, node to line, the grade, material, the section. So I am creating one more section here. Pile of suppose 0.8 meters. Okay. I'm going to choose pile, and the distance is -1 10 number of times, and that is my first one of 20 number of times. Apply. This is my first, and then I will go to the second one. Here I will go to the 15 apply, and then I will go to 12 for the third one, apply 10. I will go rest of the 10. So Just this is just for the sake of example. I'm changing the dia of this particular pile. So if we are having a sloping ground or something like that, so we will be modeling this in this way. The main thing here is the stiffness of the soil that we are going to provide. So using this particular boundary option, point spring, and then I'm just providing some random value for the time being. Apply. So to consider the interaction between the piles and the soil, we have to provide the stiffness that we are going to get from the geotechnical team. And this is how we can model. Modeling a point does not change. We can model it in this particular changing length of the pile, something like that. So yeah. Okay, another question is what you mean by outrigger and belt and bundle tube. So I hope I have explained these in further slides in rest of the slides. So yeah, if you have further questions, kindly post that here. Okay, when modeling semi-rigid diaphragms, is a thick plate the same as a shell? Okay, so when we are going for the rigid diaphragm behavior, so at that time we do not practically model the slab, even if either as thick or thin, we do not do that, because in that time it is the rigid links that is connecting the center of mass location to all of the nodes. So that is the rigid diaphragm behavior. When we are going for semi-rigid diaphragm, so it means that we are considering the stiffness of the slab, and if there are any openings or something like that, we are considering that flexibility. So we will be providing the plates element, and that plate element, thick plate element and thin plate elements, there are two options, thick and thin plate elements. So when we are providing that as a thick plate element, so that will consider the shear deformation in that plate element as well, and in plane out of plane behavior, and thin will only be as the in plane behavior. So for the plate elements, when the thickness, when the slab for the uh, like shallower thickness of the slab, like 100 mm or something like that, we can go for the thin. But when we have a higher thickness of the plate elements, the slab, so we should be going for the thick type of plate element. If and yes, that is same as shell. When we are going for thick, so that is same as the shell element, where we have the in plane and out of plane thing. So MIDAS actually gives us one more thing, that is when we are defining the plate elements and all, and when we are going for the design part, so it does ask whether we want to consider that by considering the plate elements as shell, or we only want to consider that as a membrane element. So that thing at the time of design, we go for this mesh, auto mesh domain, sorry, define domain and subdomain. Here in the subdomain, we have this shell, wall, mat, slab. So when we define these different options, so accordingly in plane and out of plane behavior will be considered. If we go for the slab only, so it will only consider the slab out of plane thing, and shell, it will be in and out both. So which is actually used for the domes and all. Okay. Yeah. Okay, we got one more question. How to do time history analysis from Mr. Ravi Khan. Okay, so again for that, in the view of this MIDAS Gen NX, we have these different options available. One thing for the first and foremost, we have to specify the global control, whether we want to consider whether we do not want to consider geometric nonlinearity. So we'll just go for none, large displacement, P delta, whatever you want to consider. And then the effect of the loads before performing the time history analysis, we will set up that thing here. And then we go for the load cases, add. Here, it can either be linear type or non-linear type of time history analysis. So that is modal, direct, and transient and periodic type. When we go for the non-linear, it can be modal, direct, static. Yeah. So non-linear static is nothing but a pushover analysis. And then we go for defining the end time, whatever ground motion that we are selecting. When it is ending, that end time we specify here. The increment of that, that suppose I am entering it has 10 seconds, and then at each 0.01 second of that 10 second, we want the results, and step number increment for the output. So at each and every step, like at each 0.01 second, 0.02, 0.03, 0.04, or by skipping the 4 increments, it will give us the fifth one. So we can set out those parameters here. And what is my damping ratio, that we can specify here. So this is the load case that we are specifying here for the time history analysis. Then we go and select the time history function, add time function, earthquake. And here in the MIDAS database, we have these many time history cases, ground motions. Okay. So either we can directly use it, and if we have any other ground motions, we can import it as well, or we can enter the data here. Just copy from Excel and paste it here, so it will be pasted. So we can define the time history ground motions here. And yeah, so the first step is global control, second step is to define the load case, third step is to define the ground motion. Then we go, and the application of time history has different options. One thing is the ground acceleration. Then we go to ground acceleration, and whatever load cases that we have defined, let me just define one. So this is the test name and the function. Let me define one function. Add time history function earthquake. Okay. So this is my function. I'm applying it in the X direction. Similarly, for the Y direction, apply another function. In the Z direction, I can apply another function here. And then I will just click on add. So by clicking on that, close. When we go and check in the works tree, you can see that the time history analysis, where we have the load case function and the ground acceleration. And when we perform the analysis, we can check for the acceleration value, maximum acceleration value, or the each and every step, like the 0.01 time increment, what are the forces generated in our structure. So, and when the hinges are being formed. So all those things can be checked in the time history analysis results. And there are other ways of applying this time history as well. So these 4 options for proper time history thing. Now, when we want to perform the floor vibration, so in that case, we apply that as a dynamic nodal load. So here in this particular dynamic nodal load, so I will define one more thing, and that will be applied as a force. Okay. So this dynamic nodal load of force kind of time history analysis, the function is selected, and then we can select the arrival time. So suppose I have modeled some uh, floor, like the plate element, the slab here. Then what we just do, we select the nodes where we the movement of the human being or the machine or something like that, at what node locations they are being placed. We select those nodes, and then we click on apply. So it is applied at different time intervals. So that particular function first run at this particular node, and after finishing this, it will go to the second node and third node and fourth node, and we can check like the it is moving from this to particular in that direction, whatever nodes that we are selecting. So and that is applied as a vertical nodal load. So that is why it is called dynamic nodal load options. Yeah. So, but for our case, we can directly go for ground acceleration. We can perform the acceleration using the whatever functions that we have created. Yeah, I think we have discussed most of the questions that has been posted here. Okay, now let me just check once more. Yeah. So I think we have discussed most of the questions which have been posted. Okay, Mr. Daniel would share the recording. I think yes, this recording would be shared with you guys. Yeah. So, yep, I think that's all from my side. And thank you for attending this particular session. Yeah.
Thank you very much, Engineer Mohammed Zishan Alam, for that insightful and highly informative session. We sincerely appreciate the time, expertise, and practical knowledge you have shared with us this evening. As a gesture of our sincere gratitude for an excellent and enlightening session, we would now like to present a token of appreciation to our keynote speaker, Engineer Mohammed Zishan Alam. Please accept our token of appreciation, sir.
Thank you. Thank you very much for this particular token of appreciation. I appreciate that. And also thank you very much for all the attendees and ICE who is organizing this particular webinar series. Yeah, thank you all.
Thank you, sir. I would now like to convey the vote of thanks as we come to the end of today's session. I would like to once again express my heartfelt gratitude to our keynote speaker, Engineer Mohammed Zishan Alam. Thank you, sir, for sharing your knowledge and expertise with us during today's webinar. I would like to thank MIDAS India for generously collaborating with SLAICE and facilitating this workshop for our fellow engineers and students. We truly appreciate your efforts. With that, we have come to the end of today's webinar. On behalf of the Sri Lanka Association of the Institution of Civil Engineers and MIDAS India, I extend our heartfelt thanks to all our distinguished speakers, guests, and participants for making today's program a great success. We hope you found today's session informative and beneficial, and we look forward to meeting you again at the upcoming sessions of this CPD webinar series. Thank you all for joining us tonight. Have a pleasant evening, stay safe, and goodbye.